Hi, this is chapter 6 video of CCNA course, Network Layer. The topics that we are going to talk about in this video are the following. Describe the function of the network layer. Explain IPv4 and IPv6 protocols and a comparison between them. Relation between host devices and routing tables. Describe the common components and interfaces of a router. And configure interfaces, routers, and default gateway. The network layer provides services to allow end devices to exchange data across the network. This layer uses four principal processes. Addressing end devices. End devices must be configured with a unique IP address for identification on the network. A host is an end device with a configured IP address. Encapsulation. Network layer receives a protocol data unit, PDU, from transport layer, and then it adds IP header information, which includes IP address of the source and destination. After this process is done, the PDU is called packet. Routing provides services to direct packets to a destination host on another network. So, the packet is processed by a router, which selects paths for a direct packet toward the destination. The encapsulation. When the packet arrives to the network layer of the destination host, the host checks if the IP header matches with its own IP address and removes the IP header from the packet, turning again into a PDU for transport layer. Now, how to establish communication? The answer is protocols. The network layer has several protocols. However, Internet Protocol version 4 IPv4 and Internet Protocol version 6 IPv6 are the most implemented. Other protocols are Novel Internet Work Packet Exchange, Apple Talk, and Connectionless Network Service. Internet Protocol was designed as a protocol with low overhead and provides the functions that are necessary to deliver a packet from source to a destination. And the basic characteristics of Internet protocols are connectionless. No connection with the destination is established before sending data packets, so Internet protocol doesn't know if the receiver is present or if the packet arrived or even if the receiver can read the message. The benefit of this is that it reduces the overhead of Internet protocol. Best effort. Packet delivery is not guaranteed. Unreliable simply means that IP doesn't have the capability to manage and recover from undelivered or corrupt packets, so an error control or retransmission control doesn't exist at this level. However, upper layer services can resolve these issues, such as TCP. Media independence. Operation is independent of the medium carrying the data. That means that any packet can be communicated electrically over cable, as optical signal over optic fiber, or wirelessly as radio signals. However, a packet must have a maximum size for PDU, called Maximum Transmission Unit, MTU. The data playing layer sends the MTU value to the network layer, and the network layer has to determine the size of the packet. In some cases, intermediate devices such as router must split up a packet with a smaller MTU. This process is called fragmentation. Internet Protocol version 4 packet consists in two parts: the IP header that identifies the packet characteristics and the payload that contains the layer 4 segment information and the actual data. The IP header has the following fields. Version contains a 4-bit binary number value identifying the IP packet version. For IPv4, this number is 0100. Differentiated services, DS. It's a field of 8 bits number used to determine the priority of each packet. The first 6 bits identify the differentiated service code point DSCP value that is used by a quality of service. The last 2 bits identify the explicit congestion notification ECN value that can be used to prevent drop packets during times of network congestion. Time to live contains a counter of 8 bits that represent the lifetime of a packet. It is specified in seconds, and each time the packet is processed by a router or hub, its value decreases in 1. When the value is 0, the router discards the packet and sends an Internet Control Message Protocol (ICMP time exit message) to the source IP address. Protocol. It's an 8-bit binary value that indicates the data payload type, which enables the network layer to pass the data to the appropriate upper layer protocol. Source IP address contains in 32 bits the source IP address of the packet, and the destination IP address contains a 32 bits value with the destination IP address of the packet. Other fields used to identify and validate the packet include Internet header length. Contains a 4-bit binary value identifying the number of 32-bit words in the header. These values vary because of the option and padding fields. Total length. This 16 bits value defines the entire packet size, including header and data in bytes. Header checksum. It's a 16-bit value used for error checking. When the checksum of the header is recalculated and the result doesn't match with the checksum field, the packet is discarded. Also, when a packet is fragmented, the following fields are used to keep track of the fragment. Identification. A 16-bit number that identifies the fragment of an original IP packet. Flags. A 3-bit field identifies how the packet is fragmented, and along with fragment offset allows to reconstruct the packet. Fragment offset is a 13-bit field that identifies the order in which to place the packet fragment during the reconstruction. Through years, IPv4 has to face new challenges and has been updated. However, there are 3 major issues that already exist. IP address depletion. IPv4 has a limited number of unique IP addresses available, and the number of devices is growing through the past years, so there's a lack of number of addresses. Internet routing table expansion. A routing table is used by routers to make best path determinations. However, IPv4 consumes a huge quantity of memory and processor resources on Internet routers. Lack of end-to-end connectivity. Network Address Translation (NAT) is a technology implemented within IPv4 networks that provide a way for multiple devices to share a single public IP address. This can be problematic for technologies that require end-to-end connectivity. What does IPv6 offer? With IPv6, the previous issues were solved. The improvements are integrated security. It supports authentication and privacy capabilities. Improved packet handling. IPv6 header has been simplified with fewer fields and also allows increasing scalability and launchability. Increased address space. IPv6 addresses are based on 128 bits, which dramatically increase the number of available IP addresses, and finally eliminates the necessity for NAT because of the huge number of public IP addresses that IPv6 can hold. Now, also IPv6 have some fields. Version. 4-bit number that identifies the IP packet version. In this case is 0110. Traffic class. This 8-bit field is an equivalent to the DS field of IPv4. Flow label. This 20-bit field is a new field that allows a special service for real-time application. For example, it can be used to inform routers and switches to maintain the same path for the packet flow. Next header is the equivalent of protocol field, and it's used to pass the data to the appropriate upper layer protocol. And finally, source and destination addresses consist in 128-bit fields for each one that specifies the address of each host.
Another role of the network layer is to direct packets between hosts. A host can send a packet to itself by pinging a special IPv4 address 127.0.0.1 known as the loopback interface. It also can send packets to a local host or a remote host. Whether a packet is destined to a local or remote host is determined by the IP address and subnet mask combination of the source device compared to the destination device. In a LAN or WLAN, devices are interconnected using an intermediate device that provides interconnections between local hosts. If a host is sending a packet to a device that is configured with the same IP network as the host device, the packet is simply sent directly through the intermediate device to the destination. Beyond the LAN, when a device sends a packet to a remote destination device, a router is needed to identify the best path to a destination. This is called routing. The router connected to the local network segment is referred to as the default gateway. The default gateway is a device which manages the traffic from the local network to devices on remote networks. It often is a router. A host device does not maintain routing information beyond the local network to reach remote destination, but the default gateway has a routing table in RAM that stores route information about directly connected networks, entries of remote networks, and uses information to determine the best path to reach those destinations. The local table of the host typically contains the direct connection, that is just the loopback interface address, the local network route that are just the host directly connect, and local default route that represent the route that packets must take to reach all remote network address and is the IP address of the network interface of the router that is connected to the local network. It's important to note that the default gateway is only used when a host must forward packets to a remote network. On a Windows host, the route print or netstat-r command can be used to display the host routing table. This table contains the interface lists with the MAC address and assigned interface number of every network-capable interface on the host. The IPv4 route table with all known IPv4 routes, including direct connection, local network, and a local default routes, and the IPv6 route table with all known IPv6 routes. The IPv4 route table is divided into 5 columns which identify the network destination, that lists the reachable networks, the net mask, the gateway, that is the address used by the local computer to get to the remote network destination, the interface, that is the address of the physical interface used to send the packet to the gateway that is used to reach the network destination, and the metric, that is the cost of each route and is used to determine the best route to a destination. The destination network can be grouped into 5 sections: the local default route, default gateway. All packets with destination that do not match other specified address in the routing table are forwarded to the gateway because they are on remote networks. The loopback addresses. The addresses relate to the host and local network. The special multicast class D addresses, and the limited broadcast IP address that is used to find the DHCP server before the local IP is determined. The IPv6 route table section displays 4 columns. The if, that is the list with numbers that correspond to the network-capable interface on the host, including Ethernet, Wi-Fi, and Bluetooth adapters. The metric, which is the cost of each route to the destination. The network destination that lists the reachable networks, and the gateway. The IPv6 route section have some equivalents, like the local default route, the loopback address, or the special reserved multicast class D address. Interfaces in IPv6 commonly have 2 IPv6 addresses, a link local address and a global unicast address, and there are no broadcast addresses. When a host sends a packet to another host, it will use the routing table to determine where to send the packet. If the destination host is on a remote network, the packet is forwarded to the address of the gateway device. When a packet arrives on a router interface, The router looks at its routing table to determine where to forward the packet, directly forward or forward into the default gateway. The routing table of a router stores information about the directly connect routes that are added when an interface is configured with an IP address and is activated, or the remote routes that come from remote networks connect to other routers. Routes to these networks can either be manually configured on the local router by the network administration or dynamically configured by enabling the local router to exchange routing information with other routers. The routing table of a router is similar to the one of a host because it gives you the destination network, the metric, and the gateway. On a Cisco iOS router, the show IP route command can be used to display the routing table of a router. A router also provides information on how the route was learned, when it was last updated, and which specific interface to use to get to the predefined destination. When a packet arrives at the router interface, the router examines the packet headers to determine the destination network. If the destination network matches and a route is in the routing table, the router forwards the packet using the information. If there are two or more possible routes to the same destination, the metric is used to decide which route to use. Two routing table entries are automatically created when an active router interface is configured with an IP address and a subnet mask. The entries contains the route source, which identifies how the route was learned, like SIP. That means that it was directly connected network and is automatically created. The L is a link local route, and the S was manually created by an administration to read a specific network that is known as a static route. The destination network identifies the address of the remote network, and the outgoing interface that identifies the exit interface to use when forwarding packets to the destination network. A remote network routing table shows information about the connection with remote routers, like the route source that identifies how the route was learned, destination network, administrative distance that is the trustworthiness of the route source, the metric, the next hop that is the IP address of the next router to forward the packet, the route timestamp that shows when the route was last heard from, and the outgoing interface that is the exit interface to use to forward a packet toward the final destination. A next hop is the address of the device that will process the packet next. For a host on a network, the address of the default gateway is the next hop of all packets that must be sent to another network. In the routing table of a router, each route to a remote network lists a next hop. When a packet destined for a remote network arrives at the router, it matches the destination network to a route in the routing table. If a match is found, it forwards the packet to the IP address of the next hop router using the interface identified by the route entry, else the packet is dropped. Networks directly connect to a router have no next hop address, because a router can forward packets directly to a host on these networks. Routers. Cisco routers are designed to satisfy the needs of branch, like teleworkers, small business and medium-sized branch sites, large business organizations and enterprises, and service providers. Our routers require operating systems, central processing units, random access memory, and read-only memory. Also, a router has special memory that includes flash and non-volatile random access memory. A router has 4 types of memory: the RAM, where is loaded the Cisco iOS, the configuration file, also known as config, and the IP running tables. It also contains a packet buffer that temporarily stores packets when received on an interface of before they exit. Cisco routers also use dynamic random access memory that stores the instructions and data needed to be executed by the CPU. The RAM stores the boot-up instructions, the basic diagnostic software, and a limited version of the iOS in case the router cannot load the full feature. The NVRAM is used as a permanent storage for the startup configuration file. flash memory is where the IOS and other system files are stored. A Cisco 1941 includes connection as 2 console ports, an RJ45 and a mini USB, an aux port RJ45 for remote management access, 2 GB LAN interface for LAN access, and an enhanced high-speed WAN interface card. It also has 4 GB storage slots to support expanded capabilities, and 2 USB ports. The connections on a Cisco router can be grouped as management ports, like the console and auxiliary ports used to configure, manage, and troubleshoot the router, and the inbound router interface, like the LAN and WAN interface configured with IP addressing to carry user traffic. The most common methods for accessing the CLI environment on a Cisco router are the console, that use a low-speed USB connection, a telnet or secure shell, that are for accessing across an active network interface, and an aux port for a remote management using a dial-up telephone line and modem. But in addition, it also has an Ethernet LAN interface, used for connecting cables that terminate with LAN devices, such as computers and switches, and a serial WAN interface, used for connecting routers to external networks. When a router is turned on, it loads the IOS image file that facilitates the basic operation of the device hardware components, and the startup configuration file that contains the commands that are used to initially configure a router and create the running configuration file stored in RAM. All configuration changes are stored in the running configuration file and are implemented immediately by the IOS. There are 3 major phases for the boot up process. 1. Perform the post, power on self-test, to test the router hardware. After it, the router executes the bootstrap program to locate the Cisco IOS and load it into RAM. 2. Locate and load the Cisco IOS software. 3. Locate and load the startup configuration file or enter setup mode. It's important to mention that if the IOS image is not located in Flash, or if the startup config file does not exist, the router may look for this information through a trivial file transfer protocol. To troubleshoot a router, you can use show version command, which displays information like IOS version, RAM bootstrap program, location of the IOS, type of CPU, amount of RAM, and the last line displays the current configured value of the software configuration register, which helps in password recovery. It's important to use the service password identification, provide legal notification using the banner MOTD, save the configuration using the copy run start command, and verify the configuration using the show run command for security.
Switches and routers have identical initial configuration steps when implementing them in a network. The steps that should be completed are: assign a device name using the hostname global configuration command. Step 2. Set password. Secure privileged exec mode. Secure exec mode access. Secure virtual access similar to securing exec access mode. And finally, use the service password encryption. Step 3. Provide legal notification using the banner mode. Message of the day, MOTD, global configuration command. Step 4. Save the configuration using the copy run start command. And finally, verify the configuration using the show run command. For routers to be reachable, routers interfaces must be configured. To enable a specific interface, enter interface configuration mode using the interface type and number global configuration mode command. There are many different types of interface available on Cisco routers: Gigabit Ethernet 00, Gigabit Ethernet 01, Serial 000, Serial 001. To enable a router interface, you have to configure IPv4 address and subnet mask and activate the interface. By default, LAN and WAN interface are not activated. The interface must be activated using the not shutdown command. The interface must also be connected to another device, a hub, a switch, or another router, for the physical layer to be active. To verify interface configuration, the most useful command is show IP interface brief. The output generated displays all interface, their IP address, and their current status. Also, you can verify connectivity from the interface with the ping command. Other interface verification commands include show IP route, displays the contents of the IPv4 routing tables stored in RAM. Show interfaces, display the statics for all interfaces on the device. And show IP interface that displays the IPv4 statics for all interfaces on a router. Most routers have at minimum two interfaces. Each interface is configured with a separate IP address in a separate network. For an end device to communicate over the network, it must be configured with the correct IP address information, including the default gateway address. The default gateway is only used when the host wants to send a packet to a device on another network. A default gateway is used by all devices that require the use of a router to determine the best path to a remote destination. End devices require default gateway addresses, but so do intermediate devices such as the Cisco iOS switch. The IP address information on the switch is only necessary to manage the switch remotely. Configuring the IP address on the switch is done on the switch virtual interface. However, if the switch must be accessible by devices in a different network, the switch must be configured with a default gateway address, because packets that originate from the switch are handled just like packets that originate from a host device. To configure a default gateway on a switch, use the following global configuration command: IP default gateway 192.168.10.1. Thank you.